Today we're diving into an intriguing twist in image generation. Imagine teaching an artist by showing them their roughest sketches to steer them toward better results. This paper explores exactly that, using bad models. Not just as a comparison, but as active guides in the process. These noisier models, instead of producing polished images, generate helpful gradients that direct the refinement of better models. This technique balances realism and diversity in the final images. It's a fresh take on how flaws can actually make things better. Let's break it down and see how it all works.
Hello everyone, and welcome to our deep dive into guiding a diffusion model with a bad version of itself. If you look at the abstract on this page, you'll see the authors pointing out a big challenge in diffusion models for image generation. We often want high-quality images that match a prompt, like a class label or text description, while also preserving variety in the outputs. Classifier-free guidance is usually the technique for that. We will refer to it as CFG from now on. But CFG tends to sacrifice diversity to improve fidelity and prompt alignment. So what's the fresh idea here? The paper proposes using a smaller, undertrained version of the same diffusion model as a guide. Surprisingly, this trick seems to let the model boost image quality without losing variety. They tested it on ImageNet and got impressive FID scores, an important metric for judging image generation. Want to see how they did it? Let's keep going. Now, turning to the introduction on this page, we get more context about diffusion models. They generate images by reversing a noisy process step by step. Think of it like taking a blurry picture and cleaning it up until it's clear. This neural network can be conditioned on labels or text prompts to steer the final output. Classifier-free guidance helps sharpen these outputs and keep them on target, but it comes with trade-offs. The authors highlight two main issues with CFG. It only works for conditional generation, and it relies on a balance between conditional and unconditional processes that might not always be ideal. This sets the stage for why they explored a new method, one that can work more flexibly and address those limitations. Ready to see what it is? Let's move on. Here on page 2 upper, the discussion zeroes in on the main drawback of CFG. In short, CFG can oversimplify the images because the conditional and unconditional processes don't line up perfectly. That causes mismatches between how well the prompts are followed and how good the images look, making it tricky to dial in the exact control we want. The authors propose autoguidance, which uses a smaller, less trained version of the model to guide the main model. It sidesteps the misalignment issue and works for conditional and unconditional tasks alike. They tested this on ImageNet, and the results look strong, setting new benchmarks in fidelity and diversity. They also plan to release their code and pre-trained models, so keep an eye out for that. Now let's explore the mechanics of how these diffusion models do denoising, as explained here. The model starts with a noisy input and progressively makes it clearer in each step. It's trained to predict either the clean image or something like a scoring function that helps guide the denoising process. The training objective is basically to shrink the gap between the model's prediction and the ground truth. When we do conditional generation, like specifying a certain class label, the model uses those labels to produce matching images. Classifier-free guidance then refines it by blending the conditional and unconditional outputs. The guidance weight is a dial you can turn. More alignment means clearer, more canonical images, but less variety. This is the balancing act that auto-guidance tries to improve upon. Here on page 3 upper, we see a deeper look at classifier-free guidance. CFG modulates how much the model focuses on conditional versus unconditional cues. By tuning a weighting factor, you can push the output closer to the desired label, while keeping some diversity. But there's a downside. CFG can distort the sampling process, sometimes causing oversimplifications or oversaturation. Why does this happen? Because CFG isn't perfectly aligned with the actual data distribution. It's like pushing the model too hard into certain directions, which can create subtle inconsistencies. This sets up the big question. Can we guide the model without warping what it's learned about the underlying data? The authors say yes, and that's part of what autoguidance aims to solve. Still on page 3, the authors explain why CFG tends to improve quality. An unguided diffusion model can sometimes wander into unrealistic images. it doesn't stay tight within the core of the data distribution and ends up generating oddball samples. By focusing more on the conditional part, CFG keeps the model from drifting too far. This yields sharper and more coherent images. The trade-off, though, is reduced variety. The model zeroes in on the safe zones of the distribution, making outputs look more canonical, but less diverse. Now let's check out the figures on page 4 upper. See how the fractal-like dataset is split into 2 regions? Look at figure 1 here, if you have the paper in front of you, to see a clear separation in the ground truth distribution between 2 classes. Without any guidance, diffusion models produce scattered samples that miss the mark. Classifier-free guidance does better, but can over-concentrate on the main class, losing diversity. Naive truncation tries to force samples into narrow spaces, but it's not flexible. Then we see autoguidance come in. It balances the process, avoiding those pitfalls, and offering a distribution that's closer to the ground truth. The second row in figure 1 visualizes the probability functions, showing how autoguidance nudges samples toward the right place while preserving variety. Page 4 lower gives a zoomed-in view of the diffusion process at a mid-noise level. These density plots take a look if you can show how guidance strategies concentrate samples around the correct data distribution. Gradients essentially pull points inward. CFG steps in by filtering out outliers, focusing on the core of the data. A key insight is that one network handles all classes, while another deals with just one, making alignment more feasible. This difference reduces errors and boosts image quality. Notice how this ties to the core idea. By comparing how 2 models differ, we can refine the sampling to be more accurate. That's precisely what autoguidance aims to exploit. Now on page 5 upper, the authors clarify that CFG isn't just about matching a specific class label. It's also introducing a force that compares 2 density estimates and steers data points inward, reducing outliers. So CFG kind of acts like adaptive truncation. It ups the likelihood of plausible samples and avoids over-smoothing. It stays away from naive solutions like just making score vectors longer, which could degrade image quality. In essence, CFG is a neat balancing act, but the question persists. Can we do better without some of its inherent limitations? That's where autoguidance continues to come into play. Still on page 5, the paper introduces the main star, autoguidance. It's basically a strong diffusion model guided by a weaker version of itself. The weaker model might be undertrained or smaller in capacity, intentionally so. The difference in their predictions is used as a signal to push toward better samples. When the 2 models agree, autoguidance doesn't do much. But when they disagree, that disagreement nudges the strong model to improve. One reason it works well is that the weaker model's errors are consistent and predictable, so the system can systematically correct them. It's a clever twist on using a bad version of yourself to get better, which is the paper's main theme. On page 6 upper, we see how the authors test autoguidance using synthetic degradations. They purposely introduce corruptions, like extra dropout or noise, into a high-quality base model, then use that corrupted version as the guide. Curious how it performs? It still guides the main model effectively, mostly undoing the damage caused by the added noise. The big takeaway is that for autoguidance to work, both the main and guiding models need to share a similar type of degradation. If they're mismatched, the results aren't as strong. But if you control the corruption carefully, autoguidance can recover much of the original quality. Now on page 6 lower, the authors shift to the main benchmark. ImageNet at 512 x 512 and 64 x 64 resolutions. They compare their approach to top diffusion models. The guiding model is weaker, trained for fewer iterations and/or with fewer parameters. Despite being bad, it greatly boosts the main model's image quality. They measure improvement through the FID metric, a standard test for generative quality. For ImageNet 512, FID drops from 2.56 to 1.25 with the largest model. That's a big improvement in fidelity, and it also cuts down on the required compute. Turning to page 7 upper, we see a detailed table. Check it out if you have the paper, comparing performance across different diffusion model configurations on ImageNet. The table shows how various guiding models, including those with shorter training or smaller capacity, can significantly reduce FID scores. The best case? A smaller guiding model applied to the largest main model, yielding an FID of 1.25 on IMAGENET 512. This sets a notable benchmark. There are also plots showing how training duration, capacity, and exponential moving average parameters affect performance. They illustrate that autoguidance can work well in many settings. Still on page 7, the focus shifts to how sensitive autoguidance is to different parameter choices, and how it applies to both conditional and unconditional diffusion models. Looking at the graphs here, you'll see that changing guidance weight, model size, or exponential moving average settings can alter FID scores, but autoguidance consistently offers better results than CFG alone. There's a new record on ImageNet64, an FID of 1.01. Even the unconditional models benefit. For instance, an unconditional model's FID went from 11.67 down to 3.86, a dramatic boost. This suggests autoguidance could be helpful in scenarios beyond standard conditional tasks. Now glance at page 8 upper for some side-by-side images. They compare classifier-free guidance versus autoguidance for categories like tree frog, palace, mushroom, and castle. If you look at these figures, you'll see how higher CFG weights can exaggerate features, sometimes making images look unnatural or oversimplified. In contrast, autoguidance keeps them more realistic, while still highlighting key details. So it's a balancing act. You want clarity from guidance, but you don't want to lose all diversity or produce cartoonish shapes. Autoguidance seems better at maintaining that sweet spot. Page 8 lower discusses training strategies and more visual outcomes. The authors note that cutting down on training data for the guiding model doesn't help much, but matching the degradations between the main and guiding models is crucial. If the synthetic degradations don't align, performance gains vanish. They also compare CFG versus autoguidance on real-world images. CFG can produce more canonical, but less varied results, whereas autoguidance keeps the nuances. For instance, a building scene stays richer in detail under autoguidance, rather than collapsing into a simplified structure. Flipping to page 9 upper, there's another visual comparison. Both CFG and autoguidance are tested at different guidance weights on a prompt involving a bird and a basket of items. As you turn up the guidance weight, CFG images become clearer but lose diversity. They start to look repetitive. With autoguidance, you still get clarity, but you also keep more variety in composition and style. The images feel more distinct from one another. So if you're looking at figure 2 here, notice how autoguidance images don't all collapse to the same layout. That's a big plus. Moving further into page 9 lower, the authors apply their approach at a larger scale using Deep Floyd Infinite Fidelity, which is a text-to-image model created by Stability AI. Classifier-free guidance again struggles to juggle style, detail, and diversity all at once, sometimes oversimplifying the outputs. Autoguidance, however, holds on to visual complexity while enhancing quality. You can see examples of intricately built castles that retain rich stylistic touches. They also mention the possibility of combining autoguidance with existing methods, distributing guidance weights more adaptively for more artistic control. Hints at broader creative applications for the approach. Finally, on page 10 upper, we look at future directions. The authors talk about formalizing autoguidance by clarifying when it's most effective. They propose guidelines for choosing guiding models. Ideally, smaller snapshots of the main model, but large-scale generators are trained in stages, which can create distribution shifts that challenge these assumptions. So there are still open questions. What if the distributions drift too far over training? How do we handle that? The authors suggest these issues should be tackled to make autoguidance more widely applicable. And that's where the paper leaves the door open for further research. And that brings us to the end of our deep dive today. We covered the main ideas, the experiments, and their implications. Hope this gave you a clear picture of how autoguidance uses a smaller, less trained model to refine a larger one, all while preserving diversity and boosting image quality. That's an intriguing technique that opens up plenty of avenues for future study. Thank you for following along.